Yes, so we'll begin. Any questions from the last section? Yes, Shiny had a question. Merging of task and optimization. Let me see the lecture first.
4 or 5 or 6 can implement A, this function A. Similarly, UB is 1, 3, 7. This is a toy problem, absolutely toy problem that I am showing you. C is 4, 5, 6, 8. And D is most flexible, can be done by 1, 2, 3, 5, 7, 8. So for each of them, these are the candidates. Okay? Right? Now, so E for similarly, if the time penalty is false, fitness is reduced. Partitioning version of the concept. Switching over it will be reduced wherever I can mark the task. We can show that it was based on the availability of a good library, which had the different costs mentioned. Typically, or ideally, it should also have the power cost of the hardware devices that are there, should be mentioned. But in our experiments or the discussions that we have done, some optimization. Till now, we have talked about the architecture level hardware, discuss those. Got a task graph. All right, you can see that's P3 and P4. I can mark these to be P3 star. What is the advantage? Advantage is if you think of the overall computation time, whenever a task ends, another task starts, then there is a context switching over it from the up to more. For example, here, again, the same graph, but suppose this task T2 needs a particular data. Now, till that data comes, T2 is health part is not, but it's probably possible to break up this T2 in.
Yes, Shiny. Yes, Popin, I'll explain SAP and ALAP. I'll first explain to what Shiny was asking. So just let me know if you are able to see my screen. Yes, I hope you are able to see my screen. So what happens is there is something called context switch. Okay. So what it is, let's say you have okay, yeah. Let's say you have task 1, task 2, task 3, task 4, like that. Okay. Now it has got code 1, code 2, code 3, code 4. Now let's say that uh, all the 4 tasks are running. Okay, T1, T2, T3, T4, they are running in round robin fashion. So what will happen? First T1 will run, it will take some time, let's say the value is delta T. Then a time will be spent which is just a fraction of the total time, delta Ts, which is called the context switch time. Okay, which is called the context switch time. Now what happens is after this T2 will run again for del T, and then again delta Ts will be there, which is called the context switch time. So context switch time is the time taken to switch between tasks. Okay, so what is happening now is you see the total time period of the total execution time of all this task is T1 plus T2 plus T3 plus T4, which is delta T into 4. But you also have this switching time, right? So which is delta Ts into n minus 1. So the total time that is taken for all the tasks to run is T1 plus T2 plus T3, which is can be also written as summation of T, sorry, just hold on, yeah. Summation of Ti, I from 1 to n. This is the total time of the execution of the task plus n minus 1 into del T. Okay. So you see this term is an extra overhead that is more than the number of tasks, okay, that is required over and above the task execution. So this n minus 1 into del T, you can reduce it how? By reducing the number of tasks. Let's say instead of, so the total time here will be 3T because n is equals to 4. You have 4 tasks. Now let's say you reduce the number of tasks. You keep the functionality same, but you reduce the number of tasks from T4, 4 tasks to 2 tasks. Okay. Then what will happen? What is the value of n? The value of n is 2. So you have this total time execution of task, which is T1 plus T2 plus this del T into 1. So right now you have reduced the time of 3 del T to del T by merging the task. So this is called as merging of tasks. Okay, is it clear? Shiny, are you there? Is it clear? Okay, pop in, let me see. ASAP, can you tell me which lecture it has? In which lecture can I find ASAP and ALAP? Pop in, are you there? Let me write. ASAP lecture 42. Okay.
we have seen in the lecture till now that we can do some optimizations and reduce the subtraction done at the same control step. If I want to have them done, this was being shown here, that the schedule that I do will also have an implication on the number of functional units that I'll be needing. So it's coming here. As soon as before this, why? Because it is consuming data. I'll try to schedule it, although the data is available, I'll schedule it as late as possible, say immediately now everything is available, so I have to do this, and I was delaying this further, so I do the multiplication here. This is as late as possible, this is as soon as possible. So if we look at this, how does it look like? Now here in the CDFG, unlike the FSMG, where we had shown all the data operations explicitly, what we do here, we only show the operators or the operations. We only show the operations. Okay. So absolute finding of A and B. We are starting with A and B. A and B are coming as input here. Min, max, shifting, addition, subtraction, max computation. Then we send 1 to done as a controller output, and the output comes here. Right. And that is my CDFG. So this entire thing can be transformed into a CDFG, where I just look at the data. Here are two schedules. You look infinite, right? So now let's move to the scheduling proper. So as I say, scheduling means assigning clock cycles to register transfers. Now this is important. What I mean by register transfer, if we look at it as a if I look at it as just in the last step of our earlier lecture, when we allocated the variables to the registers, we could see that all the operations could be represented in terms of data transfer across registers. We can have different types of scheduling. One is non-constraint scheduling. There is no constraint. You just do some scheduling. And there we have got two very popular, ASAP and ALAP. ASAP means as soon as possible scheduling, and this one is ALAP is as late as possible scheduling. All right. We will also see some constrained versions of such scheduling. And we will particularly see two types of constrained versions. One is resource constraint, RC, where what we mean is, given the number of resources are known, there is a time constraint scheduling, where given the time, we minimize the resources. We have to try, already told you. So based on that, you have to reduce, you have to see how fast you can do it. Still, look at a different guys. And here we show, unlike the FSM, shifting, addition, subtraction, max computation, then we send 1 done. Here are two schedules formed into a CDFG, where I just look at the data. The variables are not shown here, you see. The variables are not shown here. Here, the variables are data that are flowing along these data edges, data flow edges. Okay, the data is flowing along with these operators. Now, given this, here are two schedules. You look at this one. This is our CDFG, this one. And what has been done in this case is the ASAP schedule as soon as possible. So what we did, whenever, what do we mean by as soon as possible? Say whenever I have got the data for a particular operation ready. Say for example, there is an operation add, and there is no further dependency on this. Say here, the data is available, I schedule it. All right? And there is another operation which is actually dependent on this, maybe multiplication. Now, once this data is available, I can schedule it here, or as since the data is available, I can do it much later, because the output of this is required maybe much later, maybe with some divider, something of that. It's coming to another path with some other graph.
Yes, pop in. So I'll tell you exactly. I understood. So let's say that you are doing one operation which is called a plus b equals to c, and then you are doing several operations here. Okay, some ops. Okay, many operations here, and then you are doing d equals to c into e. Okay. So so here the idea is that ASAP means whenever A and B are available, you compute C. Okay, and A lab means which is as late as possible. What it actually means is, see, even if C is available, C is required only in computing D, right? Now D needs to be computed after all this operation. So you can shift this operation to here, C equals to A plus B. So what you are actually doing is, you are shifting the operation or shifting the result of this operation much later in the code. Okay, so that it need not be dependent on A and B, because it might happen that when C equals to A plus B is getting calculated, at that time A and B is not available. So what will happen is this code will wait for A and B. Okay, this code will wait for A and B till A and B are available, and then it will compute C. So this is an extra time, okay, that is getting consumed. So what if you use this extra time in computing the other operation, and you shift this operation C equals to A plus B to here? When you shift the operation from here to here, what will happen is, now A and B are readily available, right? Because A and B are not getting computed, because the operation is not waiting for A and B. A and B is right now available here. So C equals to A and B, and then you compute D. So this is called as late as possible, and this is called as soon as possible. Most of the time, as late as possible gives better results. Okay, this is important. Is it okay? Open, is it clear? Yeah, see, when we will do hardware and software partitioning, it is, for example, let's say you have parallel hardware running. Okay, when you have parallel hardware, you can assign some task to the parallel hardware. At that time, you do hardware partitioning. In software partitioning, what happens is, you have the same hardware, but let's say you have different processor. At that time, what will happen is, you can partition your software into different processes, and you can give to different processor. And then, you can parallelly run those processes. So this is called as software partitioning. In hardware partitioning, you keep the functionality separate on two separate hardware itself. Okay, so that both of them compute parallel processing. And what is important is, the failure of one of the hardware will not affect the other hardware. Then we can do hardware partitioning. But if there is a requirement that failure of one of the processes can affect the other process, at that time we do software partitioning. Is it okay, Havya? Oh, Bhavya is not there. Okay. So, any other question, please ask. I'll come back in 5 minutes. Bhavya, are you there? Is it okay? Oh, acha, okay, fine. So, any other questions? I'll come back in 5 minutes. अच्छा, कंप्यूटर इंफॉर्मेशन शुरुआत करेगा. शुरुआत बोलती श्रेयस. हां, ঠিক আছে. তুই ইএমসি তে নাকি কিছু পাসনি এখনো? আচ্ছা, ঠিক আছে. ঠিক আছে. না, আমি ল্যাবে নেই. তুই শ্রেয়াসের সঙ্গে একটু কথা বল. Yes, Aditya. Aditya, are you able to hear me?